Good afternoon, everyone. Everybody having a good week? Been busy? There's nothing wrong with busy. That's good. So, what's different about today than the previous 3 times we've come to class? What observation can you make that I've changed? I got something up here, don't I? Yeah, what do I have up here?
Some kind of liquid.
Some kind of liquid? In what? If you were to describe it to somebody, I think I heard somebody say it. What do I have up here? Have some sort of flask, right? Has some sort of liquid in it, right? What else can you tell me about it?
It's got a brown top.
It's got a brown top, okay, so it's got some sort of little stopper in there to keep the liquid in.
The liquid is slightly brownish. I mean, slightly yellowish.
Slightly yellowish, I'll buy that. Yeah, it kind of looks a little yellowish. When you hold it up to the light, maybe it's kind of hard to see, but yeah, there's a little bit of a yellowish tinge to it. So, what do you suspect it may not be? It may not be pure water anyway, right? There, so, okay, we're making some observations here. What else can you tell me? There's people in the back. What else can you tell me?
If it is an aqueous solution, the thing that's dissolved in it is solvable by water. So
Okay, if there's something that, whatever's in there with the water, if it is water, it's something soluble, right? It's a solution. Right. Okay, what else can you all tell me? Is the flask full? Half full of?
Or half empty.
Of the liquid. Let's just call it the liquid right now. We don't know for sure that it's water, right?
that is
Yeah. So that means that there's some vacant space in there, right?
sure.
Pardon?
Sure.
Yeah, okay. What else can you all tell me about it? Anybody curious about what might be in there? You're kind of curious? All right, so how can we determine maybe what's in there? So we got a curiosity, we've made an observation. Take a swig? That'd be a smart thing to do? No, but we could do that, right? Right, if it was maybe in a regular cup, and you trusted that it may have come out of the kitchen, you might go, well, let's taste it and see what it is. I would not recommend anything in a 500 milliliter round bottom flask to be tasted, but we're starting to probe what it might be, right? That's a physical property, taste.
Smell.
Smell, we could maybe open it up and smell it, right? Yeah. I mean, I've got that thing here, and I'm just taking a look at it, and oh wow, huh? Something kind of happened there. Something happened there, huh? What did I do?
You shook it.
I shook it. Shake your bottle. Does it turn blue? Don't shake the cup. Right? But it turned blue, right? Yeah. Turned blue. What else can we say about it?
What happens when we shake it again?
What happens when we shake it again? Is it still blue?
Probably.
Is it still blue? Is it the same blue as it was when I shook it?
It's
Blue now? Oh, now it's lighter. Now it's back to it kind of looks yellow again, doesn't it? Well, guess what? That definitely isn't water, right? Anybody in here got a water bottle? Shake it. Let's see if it turns blue. That turned blue. Now would you drink it?
Yeah, no.
Oh, you don't know. I highly recommend you not shake it. Right? So, somebody said something about maybe we shake it again, right? If we do an experiment and we see an observation, a change, should we just take that at face value?
You could.
You could. Is that what scientists do? No, so I should probably shake it again. And in fact, it turns blue again. You think it'll stay blue this time? What's a prediction?
Probably revert back.
Probably revert back, and why are we making that assumption?
Because it's getting once before.
Because we saw it. Is there any physical law of nature that says it must go back? No, not at all, right? So we're gonna see if, we just redid the experiment, we're gonna see if we get the same result, aren't we?
Well, we're trying to find out if there is a law that says it must go back.
Okay.
Looks like it's getting darker
I
now.
think it's getting darker now.
It did that last time too.
You did that last time?
Darker than lighter.
It didn't take.
Did it take that long? So you've been kind of keeping track of the time a little bit?
Yeah, every sport.
Every second? Oh. But you might be measuring how long it takes to change back to a color, right? Is it getting darker or lighter?
The lighter.
Getting lighter, it's going back. So what does that suggest for us?
It's gonna keep getting.
Suggests that that's probably going to keep happening, right? And so now I would argue it's back to where it was again, right? So good chemists, good scientists like to do experiment at least 3 times, right? So let's do it a 3rd time. Voila, it's blue. Now that is a curiosity, isn't it? It's something that's making us shake our heads just a little bit. Why is it that a bottle of seemingly clear, maybe slightly yellowish liquid, when it gets shaken, why does it turn blue? And then when we wait a while, it goes back to another color.
Kinetic sensitivity.
Kinetic sensitivity, maybe? Okay. What else? Form some hypotheses for me. What do you suspect is going on? A type of chemical reaction. We think it's a chemical reaction. So chemicals, they can react by themselves, but typically there's more than one thing involved in a reaction, right? Not always, but typically. What might the other thing be? I'm sorry.
Something dissolved in the liquid.
Something dissolved in the liquid, okay? And that something, under certain conditions anyway, must be colored.
Maybe that's 2 liquids.
Right, but now wait a second, I'm looking at that liquid and everything in there looks to be homogeneous. I don't see another layer, I don't see other things floating around, I just see a solution, right? So if whatever this thing is reacting with, let's see if I can get that in the camera, so keep watching it at home. Watch the blue bottle turn blue, right? It goes colorless again, right? It seems to be doing that over and over again. Right? So there must be a substance in there that when it reacts with something else turns blue. What are blue? Can you guys give me an idea of things that are blue? Blueberries? Okay, what makes blueberries blue?
Sometimes light.
Huh?
Light.
Well, the light is the result of why we can see, right? If I turn the light off, that would no longer be blue, right? We wouldn't be able to see it. That's true. What do you think? What's been in the news lately about people's health? Dyes, right? So maybe I've got a blue dye in there, right? Well, how many of you have ever baked or anything and used blue dyes or tie-dyed something, right? You add the dye to the water, did it go colorless?
Normally it stays.
Normally it stays that color, right? But apparently probably I added a dye, right? We know that dyes are colored, but when I shake it, it turns colors. Imagine having a shirt that when you moved and shook it, changed colors. Wouldn't that be cool? Yeah, that'd be cool, huh? So apparently everything must be in solution because I don't see 2 layers. So what's it reacting with?
Does that have something to do with the gas in the bottle?
Ah, is that space above it empty? No, one of the things we say sometimes when we have an empty cup is we say the cup is empty, but in reality it's full. It's full of what? Air. It's full of air, right? When you pour a liquid into it, you displace the gas with the liquid. But an empty cup ain't empty, right? So I've got liquid that's filling up about half of it, and the rest of it is probably air, right? And so when I shake it, what's happening?
The water is mixing with the air.
Okay, and what does that do?
Cause a reaction with 1 or 2 of the solvents within
Well, something that's in there,
the
yeah.
liquid.
Okay. What else? What is air? It contains oxygen. Is it pure oxygen? No. What else is in air?
Nitrogen.
Nitrogen. Is that it?
Carbon.
We've got carbon dioxide, right? We've got a little water
A
vapor.
little bit of hydrogen.
And a little bit of other elements, right? But the biggest chunk of the atmosphere is nitrogen and then Oxygen, right? So what do we know about oxygen and nitrogen when we look at the periodic table?
They're right next to one another.
They're right next to one another. That's true. Very good observation. What do we know about the reactivity as we move from left to right within a period of the periodic table? Do we become more reactive or less reactive? In other words, is nitrogen more or less reactive than oxygen?
Less.
Nitrogen is less reactive than oxygen, right? We typically consider it less reactive. So if we were to hypothesize, what might we say is probably most likely for turning blue?
Oxygen.
Probably the oxygen. We would make that. We would form that hypothesis, right? Seems like a reasonable hypothesis. How could we test that hypothesis?
Well, we can make one, or I say we can make one. You could put a flask with nitrogen in whatever that liquid is, and then one with pure oxygen. I'll see what happens.
And-
Now, if our hypothesis is correct, and I displace this gas completely with nitrogen, and I close it and I shake it, what would we expect?
Nothing.
Yeah, we'd just shake it up and nothing would happen. It wouldn't turn blue probably, right? If our hypothesis is correct. If I replace it with oxygen and shake it, what might we expect? Turn blue. Yeah. And in fact, I can tell you the results of this experiment because I've done exactly this experiment. You shake it with nitrogen or carbon dioxide in it, nothing happens. It's just, you're just shaking a bottle with liquid in it. You put pure oxygen in there and you shake it just a little bit, and it turns blue and it stays blue for days. So that's interesting. If I put pure oxygen in there, it stays blue for days. But if I have a mixture of oxygen and nitrogen, it doesn't stay blue. What's up with that?
Probably the same thing that happens with soda.
I'm sorry, I didn't understand.
Probably the same thing that happens with soda.
With soda? In what way?
Like it goes flat if you leave it open.
Okay, yeah, we can have gases that escape the liquid, right? Like a soda going flat. That's certainly true. What else? Yeah,
Can I say hypothesis for why?
you can. In fact, I want you to. Yeah, we need to form a hypothesis, right?
My hypothesis is that when things are oxidized, like iron or whatever, they change colors.
Ah,
They
very
get-
good.
They turn to a different color, and different oxidation states have different colors. Perhaps whatever is in that liquid gets oxidized.
With the oxygen from the air?
And over time, the oxidation state breaks down as the solution settles
Okay,
and turns back to its original color.
all right. All perfectly good hypotheses, all testable. What is one of the rules of a hypothesis?
Gotta be tested.
It's got to be testable and it has to be falsifiable. Very important. That's the difference between scientists and quacks. Okay? A scientist, we have to be able to falsify something, to prove something. It's very hard to prove something. Very easy to falsify something, right? And so we are skeptical chemists. Going back to 16 whatever with Robert Boyle, right? This idea of the scientific method. Okay? I will just tell you what's in the bottle. The bottle is very simple. The bottle is water, about 300 milliliters of water in there. There's 10 grams of dextrose. What's dextrose?
Sugar,
It's a sugar.
fine sugar.
It is a sugar. There's 8 grams of potassium hydroxide. What is potassium hydroxide?
A salt.
It is a salt. What kind of salt is it? Anybody know? Is it an acid? Is it a base?
Acid.
Hydroxides are bases. So I've got a basic solution of sugar water, and then I added a few drops of what's called methylene blue, a dye. I added a little bit of methylene blue to it, okay? And what happens is, in the sugar, dextrose is what we call a reducing sugar. You're going to learn about that in biochemistry. It reduces things, and it actually reduces the methylene blue to what they call methylene white, which is that. So as long as there's no oxygen in the water, and you got plenty of sugar, a little bit of base, you need a little bit of base to make this work, it will reduce the methylene blue to methylene white. And it won't be colored. Now when I shake it, what am I doing? I'm introducing oxygen into the solution, just like the fishes need to breathe, right?
Yeah.
And what happens then? I oxidize the methylene white back to methylene blue. There's oxidation and there's reduction. You don't need to know all of that today for class. You'll learn this over time. But we've made an observation. We got interested. We started forming a hypothesis. We actually determined some ways in which we could test that hypothesis. So, as I mentioned to you on day 1 in this class, the scientific method is very, very important. Science. It is all about the scientific method. It is not about doing cool things in a laboratory. It is not about taking samples from patients and seeing what's in them. The scientific method is what makes science science. Okay? So, what are the steps to the scientific method? We kind of discovered most of them here, not all of them. We make an observation about nature, right? Yeah, we make some sort of observation. We observe. To be a good scientist, you must have good observational skills. Most of the things that I am most proud of in my career were things that happened by accident. But I didn't get angry and say, that didn't work. I wonder why that didn't work. I asked a question, I made an observation. I went down a rabbit hole. Okay? So, we made an observation. Then what? What did we start doing after we made the observation? We did make hypotheses, but before that we started to ask maybe more general things. We started to ask questions. And those early questions that we asked probably weren't hypotheses yet, right? But they were close. So questions, hypothesis, right? So you start to question what's going on. That is the most important thing that you will take away from college. Isn't the answers that you leave with, but the ability to ask important questions. Questions are more important than answers. How many of you believe what I just said? Questions are more important than answers. Why are questions more important than answers?
It shows that you're comfortable enough with the subject to have the ability to ask, I guess it would be ask questions that haven't been asked before.
Okay, I'll buy that.
We can't have answers without questions.
That is true. You need a question?
By asking a question, you admit that you don't know.
Ah, that's right. We're starting to expand our realm of knowledge, aren't we? Yes. Can't have answers without questions. Your comfort level with the material, right? I want you to, when you graduate, I don't care what you go on to do in life, it's your business. I want you to ask good questions. I want you to be a questioner. Question authority. Question reality. Question the science. Question, question, question. Demand answers to your questions. Study those questions. Be curious. Curiosity is what led to medicines, materials, our modern way of life. Okay? And then we get more questions as we go on. Okay, so now we ask questions, and then what do? Not all questions are testable, right? But we have to have something that's testable, and we call that a what? Hypothesis. What is a hypothesis? Pardon? It is a testable question. It is a testable question. If I cannot test it or falsify it, it is not a hypothesis. If I cannot question it, or test it, or falsify it, it is not science. You start to get into the realm of pseudoscience and conspiracy theories. It exists. That does not mean that conspiracy theories don't have truth to them. There's a lot of conspiracy theories that ended up being correct. Okay? But it's not science until you can have a verifiable, a falsifiable hypothesis. Okay? What were some of our hypotheses?
hypothesize that if we were to substitute the oxygen inside of the fluids for nitrogen or carbon dioxide, it would not have the same result.
Okay, yeah, we started to make hypotheses about what was reacting in the system, right? We did. Are those testable? They are testable. I can go into the lab and I can do that, right? Are they falsifiable? Absolutely. We hypothesized that if we put nitrogen in the flask and shook it, it wouldn't turn blue. Right? So if I put nitrogen in there and it turns blue, that's clearly falsified, right? Same way with oxygen. If we put oxygen in there and shook it and nothing happened, we would have said that hypothesis that the reaction between the dye and the oxygen was falsified. Okay. So, step 4 is test, right? We have to be able to test and falsify. I'm not asking for a show of hands, but I want you just to mentally raise your hand, if you will. How many of you have ever in high school written a paper or whatever and then changed your mind at the end and just went back and changed your opinion on everything? Right? Is that science? That's not science, right? What is science, though, is having a test, a hypothesis, and then trying to falsify it. If you cannot falsify your experiment, it is not a good experiment. And everybody, and I do mean everybody, is tempted to construct their experiments to prove their hypothesis. So when you all start doing research, or you go to medical school, you go over and somebody says, you know what, if I did this, it would prove my hypothesis. Is that the right way to think about it? No. Well, if I put oxygen in there, that would prove that this is happening. Is that the right way to look at it? No. Right? We have to look at it in a way that's clearly falsifiable. If you cannot falsify your hypothesis, then you're not doing science. That is a true statement. Okay? It's a universally true statement. What else do we do? Is it just one test?
No.
Repeat them.
We typically repeat them, right? So scientists will typically, we repeated the experiment at least 3 times. At least I remember shaking it 3 times, but we might have done it 4 or 5 times. Okay? Right? And we got the same result. Right? What else do we do when we're doing these tests? We record things. We take notes. We make measurements. How could I have measured some of this? Pardon?
Time.
Time what? What time?
The time it took to revert back to its original color.
Okay, so we could test that right now, couldn't we? So, get out your stopwatch. Everybody got a stopwatch going? And when I start shaking, hit go. Ready, set, go. Let's turn blue. And let's see how long it takes it to go back white. You all tell me when you think it's done.
Done.
All right. Every one of you have the same time?
I had 51.28.
You had 51 and change? What'd you have?
49.
49, what'd you have? Or you didn't have time. Who else had time remote? You had time remote.
I had 50.
50.
51.65.
51.65.
59.7.
59.7.
I don't know what.
Okay. Anybody else?
48.7.
48.7. What does that just demonstrate to us?
Human error.
There's error in every measurement we make. Do we need to take that into account?
Yes.
Absolutely we need to take that into account. You're going to start learning that.
And you can make inferences from data after you have enough.
Absolutely, yeah. We could actually start to test different questions with this, right? We could make predictions about the future. The prediction that you made right now is that if I shake it and set it down, it's going to take about just under a minute for it to turn back to methylene white, right? If I come back tomorrow and shake it, do you think that'd be the same?
Yeah, probably.
Yeah.
Might be.
Might be.
Is there a net law of nature that says it must be? Absolutely not. And in fact, I will tell you that tomorrow I will come in and shake the bottle and it won't turn blue anymore. Isn't that a kicker? Because all the sugar in there actually gets oxidized and there's no sugar to reduce it back to, it just, what we call comes out. Okay? It has a lifetime that only lasts so long.
No, it's
I've only got so much sugar in there, I've only got so much oxygen, I've only got so much dye. Eventually it gets all used up. Okay? It's a little more complicated than that, but that's not too far off. All right. So we might repeat our tests, right? We might make inferences. We might make predictions about the future. We might test those predictions. Okay? What else do we do? What do all good scientists do at the end of their projects?
They brag about it.
They brag about it. All right, they brag about it. I'll give you that. We brag. How do we brag?
By publishing our results.
We publish our results, right? We publish or we present. We share with the community. Scientists are not greedy people in that regard. Money's a little different story. Okay? But with our results, we like to share our results. It is bragging rights. There is nothing better than somebody coming up with a thought about how the world works and somebody coming in saying, I think you're wrong, and here's the evidence to show why I think you're wrong. History is full of that stuff. Chemists used to believe in this thing called phlogiston. Then we learned about electrons. And we know that phlogiston didn't answer many questions about the world. Electrons answer many more questions about the world. We used to believe that the atom looked like a plum pudding, an old British plum pudding. We know that that's not correct anymore. We used to believe that acids all gave off protons. We know that that's not correct anymore. Science is this iterative process that we hold dear. Okay? So, why did I have you read The Skeptical Chemist?
To show Robert Boyle's his scientific process.
The scientific method is the best baloney detector we've got. People all the time say to me, people like my dad, well, you have faith in the scientific method. I have no faith in the scientific method. The only thing I have in it is I know that I've tested it multiple times and it's always worked and I haven't come up with anything better. But someday one of you may come up and say, there actually needs to be another step to the scientific method, and then everything we've done before needs to be reevaluated. Okay? I don't have to have faith in the scientific method. I can experiment on it. Right? And that was where Robert Boyle, he was a skeptic. People would tell him that the earth is flat. I don't know. Doesn't seem that answers all my questions about the world. Right? And so he would conduct experiments. He worked with this recently invented air pump, pumping air. There was air in here. He could do experiments like this. Okay? Most important thing I want you to take away is the power of the scientific method. Whoop, where'd I go? There we go. Where's my modules? There we go. I also had you read Polywater. Tell me, no, come on. Yeah, we'll go there. All right. What can you tell me about this reading? What was Polywater?
It was just a hypothesis about the fact that water could exist in different what was the word? It's not polymerized, but it's just a different form of water.
Why did this cause so much concern? Why should we be concerned about Polywater?
Perhaps different kinds of water could be more or less dangerous.
Okay. Life depends on water, doesn't it? What can you tell me about water? What's its formula? H2O. It's very simple, isn't it? 2 hydrogens, 1 oxygen. What's its molecular weight? Oxygen is 16, hydrogen's 1. It weighs 18 grams per mole, right? Is that heavy? No, that's not heavy. You know that everything that weighs about the same as water on Earth except for water is a gas? Natural gas weighs about the same amount as water. It's a gas. Ammonia, NH3, weighs about the same as water. It's a gas. Do you think we could live if it was a gas? Water was a gas? Purely a gas on Earth at the temperatures we're at? No. We need liquid water. We know that all life is formed and evolved from liquid water, not from gaseous water. Right? So we know that. So they were concerned when they made this observation that water under certain conditions had strange behavior. Right? Caused a big ruckus. It was a big debate. People thought they'd found a new form of water, thought they were going to get the next Nobel Prize. How many people remember the Nobel Prize for polywater? You don't remember it because it never happened. Why is that? They disproved the hypothesis of polywater. Turns out it was most likely somebody's sweat in a capillary tube. It was contaminated. These were trained scientists. They made observations. All their observations were strange, and they couldn't explain them. And they came up with this hypothesis that we must have a new form of water called polywater. And it turns out that after further investigation, right, we falsified that. Are we sure that it was probably, or were we sure that it was somebody sweating that little capillary tube? No, we're not 100% absolutely sure. But what we know is that it's polywater, what they proposed. Somebody, one of you, one of these days may go back and look at it and determine that it wasn't sweat, it was something else, cool, but it's not polywater. We know it's not polywater. Right? Had polywater actually been in existence, people were afraid that if it got out, that the oceans would polymerize and all life as we know it would die. It sounds silly now,
Yeah.
but if you knew no better.
Well, like, it's good that what they wrote was published, because technically they weren't too far off, because there are different kinds of water
There are different kinds of water.
because of different isotopes of oxygen and hydrogen.
Okay, that's true. There's heavy water, right? There's light water. There's really heavy water. There's irrigated water. There are different types of water. We also know that water can form hydrogen bonds. You'll learn about that in Gen Chem if you haven't learned about that yet in high school. And we know that it can actually associate with other water molecules in a way that makes it like a polymer, but it's not really terribly strong, right? That's why it exists as a liquid on Earth and not as a gas. Okay? So the fact that it can do that kind of stuff is very, very important. But very, very interesting little read on polywater. All right. That's all that I had planned to go over today. The rest of the time, we're going to be looking at your semester by semester guides. So go ahead and get those up, get those out, work with your neighbor on them if you'd like. Ask me any questions you want. Your semester by semester guide is due by 5 o'clock this Friday. Okay? Also, don't forget, we are coming up, you got about 9 days, I think, to do your activities assignment 1. So get those done. Also, don't forget to go ahead and start scheduling your one-on-ones with me. Go ahead and get those going. So, for the next 30-ish minutes, I am all yours. I will answer any questions you have about your semester by semester guide. If you are going to be done and leave, put your name on the note card, and on the back, write what you liked about our little demonstration today.